Hi guys, this is Dr. Momsilovich with your lecture 10.2 on life history. So life history is the study of the timing and nature of events during an organism's life. So it's the timing of growth and reproduction and how that affects the organism. This is important when we're looking at different species to determine the health of the species as well as how quickly a species can recover from a reduction in their population number and things like that. Life history theory is an analytical framework to study the different strategies of organisms regarding their lifespan and reproduction. And this is based on natural selection. So natural selection will select for the strategy that best suits that organism. There are 7 key life history traits. And these different traits differ depending on the strategy of that organism. So the first is the size of an organism at birth, its growth pattern. So does it grow continuously, and is it spread out evenly, or is there a very rapid period of growth at the beginning and then slower growth later on? Does the organism go through metamorphosis, things like that? The age and size at maturity, so do you start reproducing young or later in life, or do you start reproducing when you're small or when you get larger? And when we're talking about starting to reproduce, it also determines the number and the size of your offspring, as well as the sex ratio of males to females in your offspring. Another trait is the age or size specific reproductive schedule. So do you start reproducing at a specific age, or do you have to reach a certain size before you begin reproducing? Next would be the age or size specific mortality schedule. So do you die at a certain age or a certain size? And then the length of your life. So how long can you expect to live? Within those different traits, there are trade-offs because there are system and energy constraints where you can't maximize all of these different traits simultaneously. You can't be huge at birth and grow quickly and become reproductive age early in life and have a ton of large offspring and live for hundreds of years. It doesn't work like that. There are trade-offs between these things that can strain an organism's ability to have lots of babies and the quality of their babies and things like that. So an organism can't maximize all of those things at the same time, and depending on the constraints for that particular organism, different things will be maximized. One important characteristic when we're talking about life history is the frequency of how often you reproduce and the number of offspring that you have per reproductive event. So organisms fall into one of 2 categories. They're either semiparous or heteroparous. Semiparity means that you have a single large reproductive event during your lifetime. So you essentially will reproduce once, produce a ton of offspring, and then die afterwards. And so we have a couple of examples for this. So agave or century plants are examples where they grow for about 10 years, and then they have a stalk that grows out with flowers. And after seeds are produced, the entire plant dies. And so it reproduces once and then it dies in its lifetime. Another example are salmon, which reproduce one time. So they will grow for usually about 2 to 3 years. Then they swim upstream back to where they were born. They spawn and they die immediately afterwards. So semiparous organisms reproduce one time, they put all of their remaining energy into that reproductive attempt, and then they die afterwards. The other category are heteroparous organisms, which have repeated reproduction. So if you have something in iterations, it means that it is being repeated. When you say like the term reiterate, I'm going to reiterate, so I'm going to restate what I said, you're going to say something again. So itero means that something happens in iterations, and this happens in a lot of species. So something like an apple tree can reproduce its apples multiple times during its lifetime. Most bird species would be iteroparous, where they can have a new clutch of offspring every year or every other year. Humans are an example of this because you can have offspring more than once during your lifetime. You don't just generally have babies and then die immediately afterwards. So remember, semelparous reproduces one time and then dies. Iteroparous are going to reproduce multiple times during their lifetime. Lifetime fecundity is how many offspring each female will produce on average during her lifetime. So we can look at this in animals, but we can also look at it in humans. And this is important because we can look at the number of offspring that women are having on average to look at the growth rate of the human population on the entire planet or per country. So in general, human fecundity rates are declining in about half of the countries in the world, where they have fertility rates that are below the replacement level, which means that those populations are in decline. So to have what we would consider a replacement level, each couple would have 2 children, so that you would have 1 child to replace each of the parents. A lot of more developed countries are actually having fewer children than that, and they're having closer to 1. So if you look at the charts on the right-hand side of your screen, you can see where are countries that are having the most children. And so these are mostly countries in Africa and parts of Asia, where they're developing nations, and for various reasons, they're having more children. So they are having between 5 and 7 children per woman. On the other hand, countries in more of the developed part of the world are having fewer children. And so in those countries, they're having usually less than 2 children per couple, which means that their populations are declining because they're not even having enough children to replace the 2 parents. And so a lot of the time it depends on the cost of having children and whether or not women are working outside of the home and things like that determine these different rates. But we can look at these to determine whether or not the size of the population of humans on the planet overall is growing or shrinking. A lot of experts are estimating that the growth rate of the human population will essentially be closer to 0 in the next 100 or so years. But as of right now, it is increasing, and it's increasing faster in developing countries than in developed countries. Survivorship curves are a graphical representation of a life table, which shows the probability of an organism of a species surviving to the maximum life expectancy for that species. There are 3 different types of survivorship curves. The first one is a type 1 survivorship curve, and this is something we see in humans, where your chance of survival is very high. And so for the first about 75% or so of your maximum life expectancy, you have a very high survival rate. And then at the end of your life, in the last 25% of your life, you have a rapidly declining chance of survival. This occurs in species that have few offspring and lots of parental care. So they're going to take care of their offspring and ensure their survival. And so it's going to be other factors that are going to be causing death later in life. Type 2 survivorship curves have a constant mortality regardless of age. And this would be something in birds where regardless of your age, you have an equal chance of survival. The third type of survivorship curve is a type 3, and this is where you have high mortality when you're young, so you produce a lot of offspring in the hopes that some will survive. Once you reach adulthood, you have a very good chance of surviving and surviving for a long time. So this would be things like trees that produce a lot of different seeds and in the hopes that some of them will survive. It would also be something like Oysters or sea turtles, which have a lot of offspring, and a lot of them are not going to survive their juvenile stage, but they're going to have a very good chance of survival once they reach their adult life form. Another life history trait is the length of life for each species. This varies quite a bit, and it varies between both plants and animals, or among plants and animals. So in animals, things can live as little as 1 day, which is something like a mayfly, which will hatch, it won't eat, it will reproduce, and then die within 24 hours. And the record for the longest living animal is Greenland sharks, which can live up to about 500 years. All other animals, hamsters and dogs and humans and tortoises, birds and elephants and whales, all those things all fall in the middle of that spectrum. Plants are a little bit different, and they actually have different terms based on how long they live, or at least for some categories. So annual plants are plants that only live for 1 year. So this would be something like a calendula plant, which produces a lot of seeds, and then it dies, and those seeds then replace in the next generation. Biennial plants live for 2 years, so this would be something like parsley, where it will live for 2 years and then die after. Other plants like Palo Verde trees can live for 100 years, saguaro cactuses 175, and then there are other plants that can live for 5,000 to 10,000 years, which are things like cypress trees and spruce trees. The length of life and the number of offspring that something has are important factors when we're talking about conservation. If we were to go down and cut down some plants, if you want to harvest some calendula, that's not a big deal because they're going to replace themselves quickly and with a lot of offspring. If we were going to go and someone said they wanted to cut down some spruce trees, that would be more of a concern because those trees have a very low probability of surviving all the way to that adult stage, and replacing that population is going to take quite a bit longer. Once we have all of this information about different organisms and how long they live and how many offspring and all of those things, we can make what's called a life table. And this shows us for each age the probability of death and therefore survival for an individual at any given age. And there's 2 different types. The first one is called a period table, which shows the current probability of death for individuals of different ages in a defined time period, such as this year. And a cohort table follows the mortality of a certain population over their entire lifetime. So they are a bit different. We're going to talk about this in a little bit more detail. So our first example is a cohort table, and this is for phlox, which is a type of flower. And this table is shown in days. And so in the first column, you can see that you have different age categories in days. So the first one is 0 to 63 days. And these plants are living anywhere from 0 to 362 days. And then from there, you have 4 other columns. So there's different variables that go into this table. X is your life stage or age class. And then the other terms have that as a subcomponent to that category. So the first one is A sub X, which is the total number of individuals that are observed at each stage or class. So for the first one, in our first category, and the number of individuals that we saw in our first group that were between 0 to 63 are 996 individuals. So that's our entire cohort. By the end, by the time we get to 362 plus days, we're down to 0. So we're following these individuals throughout their life and seeing how many of them survive to each of those different stage classes. So you can see that at the beginning, you have a pretty steady decrease in the number of individuals. So you go from 996 down to about 660, goes down to below 300, and then it sort of levels off, and we have 1 to 200 individuals until the number starts decreasing rapidly at the bottom of that at the bottom of the table. We can use that information to calculate the next 3 columns. So the L sub X is your survivorship, or your chance of surviving. The next one, D sub X, is your chance of mortality in that age class. And then Q sub X is the mortality rate for each stage or class. And so we can use the number of individuals that are surviving at each age to determine your mortality rate or your chance of mortality at that different age class. And so this may sort of sound like something that you don't need to know, and why am I making you learn this? Well, you can use this if someone you know were to get a cancer diagnosis and they were to say that you have a 75% chance of surviving, and that, but you can also then break that down into age categories and see that someone in their 20s would have a greater chance of survival than someone in their 70s or 80s. Insurance companies use something similar to this to determine your insurance rates. So if you are a 20-year-old man, your insurance rates are probably quite a bit higher than mine because I'm a 33-year-old woman. And so you could say that's not fair. I'm a really good driver and I'm probably a better driver than her, which might be true. But they look at the chance of an accident, and the chance of a 20-year-old man getting into an accident is higher than the chance of a 33-year-old woman getting into a car accident. And so they use something similar to this cohort table to look at the chance of an accident for each sex and each age category. And so this does sort of indirectly relate to your own life. So we're going to look at now how we can use this information to determine some other things. So we can use the numbers that we looked at in the last table to calculate the total fecundity for our cohort. So essentially what we're doing is looking at the reproductive rate for each category, each age category in our population. So if we look at the flocks, you can see that they don't start reproducing until they're about 292 days old. So between 292, our individuals that are between 292 days and 306 days old are having, is when we start having offspring. So the next column in this table is F sub X, which is the total fecundity or the reproductive output of the entire population for that stage class. So in this case, for that group, it's 53 individuals born in that first group. If we go down to 306 to 320 days, now we have 485. If we go down again, it's over 800 and then over 900. It drops down to about 94 and then everybody dies. But you can see at each age class, the total number of individuals that are being born for each stage class. We can then use that to calculate M sub X, which is individual fecundity or the mean reproductive output for each stage class. So for the first category where they're having offspring, there were 53 offspring born per those 159 individuals, which gives us an M sub X of 0.33 for the individual fecundity for that age class. We can then use that to determine L sub X, M sub X, which is the number of offspring produced per original individual during each stage class, which is a product of the survival and reproduction. So in this case, for that first age group that's reproducing, LX-MX is 0.05. The next group up, it's 0.49. The next one up is 0.8. You can see where we're going with this. So we're seeing as we move through this, the fecundity or the reproductive rate for each group within your table. So this relates back to this equation at the top of your screen, which is R naught is equal to the summation of L sub X, M sub X for each age category. And that tells us our net reproductive value, or whether or not our population is increasing or decreasing. So like I said, R sub O is the summation of that L sub X, M sub X, and that is your net reproductive value. So if R sub O is greater than 1, the population is increasing in size. If R sub O is equal to 1, the population is constant. And if R sub O is less than 1, the population is decreasing. And this is important when we're looking at a variety of things. So if you have a population that is endangered and your R sub O is less than 1, then you know that you need to look at different factors and see what you need to change to get that population to increase. If you have something nasty, like maybe the coronavirus, which scientists and epidemiologists actually use a version of this R sub O to look at the rate of the virus. So when newscasters are talking about this on your daily news, and they're talking about we have to get our R value below a certain number for it to be safe, this is essentially what they're referring to, is that we need to have this in few enough people that it's not going to have a rate that's going to explode and infect everyone. So if you have an R sub O that is greater than 1 or greater than a value that scientists have determined for that particular species or virus or whatever we're looking at, then your population of that is increasing in size, and we need to figure out how to get it lower. So just as a side note, I don't want you to confuse R sub O with R, or the per capita rate of increase. They are related through an equation where T is the generation time. We will talk about that more, but for right now, don't worry about that and don't confuse the two. R sub O is not the same thing as just R. So all of these different life history factors that we've talked about relate to the population growth equation, which we will get into more in upcoming lectures. I put it up in the upper right-hand corner for you just so you can see it. But when we're looking at life history strategies, we can categorize species into one of two different categories. So they can either be R selected or K selected. So R selected species, and you guys should know all of this just so you know, R selected species have a very short lifespan, usually less than a year. They have selection for early reproduction, small body size, and semal parity. So they would probably reproduce one time, have a lot of babies, and then die shortly after. There is weak competition among them. They have a variable population size that is well below their carrying capacity. And if you don't know what carrying capacity is, we'll get into that coming up. They have a very high juvenile mortality. Their mortality is density independent, and their climate is variable and unpredictable, meaning that they might have sudden bursts of population numbers when resources are good, and then their numbers go back down. On the other hand, K-selected species live for a long time, so it's going to be longer than 1 year. They are selected to have delayed reproduction and large body size, as well as be iteroparous, so reproduce more than one time during their lifetime, and therefore they're probably going to take care of their offspring as opposed to things that are semalparous. They have strong competition, so they have to be strong individuals and well fortified and be able to compete. They will have a constant carrying capacity or constant population size that's generally at their carrying capacity. They have a constant survivorship, and they have large adult mortality but low juvenile mortality. So this would be that type 1 survivorship curve. Their mortality is density dependent, so it's dependent on factors such as the amount of resources and water and things like that. And they generally live in climates where it's constant and predictable, and their resources are constant and predictable.